In this video, we'll continue interpreting NMR spectra, the information that we get out of the NMR instrument. We're going to start looking at spectra that are much more complicated like these, and in order to understand and in order to really get the most powerful information out of these spectra, we need to talk about integration and then spend a lot of time talking about spin-spin splitting, which is going to give us a tremendous amount of information about the number and types of hydrogens that are going to be present in organic molecules that we're studying by NMR spectroscopy. So we'll start with integration. This particular molecule has two sets of non-equivalent hydrogens. These 9 hydrogens, right, we have 3 methyl groups. These 9 hydrogens are all chemically equivalent, but they're different from this 1 hydrogen, right? So we'll expect to see 2 peaks. And remember, this is a little tiny peak and this is a really big peak. It turns out that if we measure the area underneath each one of these peaks, which is called integration, then the ratio of those two areas is a 1:9 ratio, which makes perfect sense, right? Because this is 1 hydrogen and this is 9 hydrogens, so that peak, the area underneath that peak, should be 9 times bigger than the area underneath this peak. Stated another way, we can say the ratio of the integrals of the 2 peaks gives the same ratio of the hydrogens. It can give us a lot of information about how many hydrogens are present in a particular molecule that we're studying by NMR. Let's look at an example. So let's say we had this particular NMR spectrum, right? We see 2 peaks, right? We see 2 peaks, and which makes sense, right? Because we would expect that we have 2 different sets of non-chemically equivalent hydrogens. We have a CH3 here, and we have a CH2 here. If we were trying to figure out which peak comes from which set of hydrogens, we might expect that this CH2 would be further to the left because it's bonded to 2 electronegative atoms, whereas this CH3 would be further to the right because it's only bonded to 1 electronegative atom directly. We can get additional information to prove that that's correct, right? Because the integration underneath this peak is 3, whereas the integration underneath this peak is 2. So we know for a fact now that this peak corresponds to this set of hydrogens, and this peak corresponds to this set of hydrogens. We know that from chemical shift, and we can verify that by integration. Okay, so up to this point, we've only talked about NMR spectra that have single peaks. These are called, in NMR speak, these are called singlets. But as you may know by now, not all peaks in the NMR will be singlets. What can happen is an individual peak can be split into subpeaks. We call this spin-spin splitting. If we look at the NMR spectrum, even of relatively simple molecules like ethyl acetate, what we see here is 4 peaks. We call that a quartet, and a singlet, and a triplet. Okay, so does this make sense? Well, if we look at ethyl acetate, we have 3 sets of non-chemically equivalent hydrogens, so we should expect to see 3 signals, right? We have a CH3 here, which will give us 1 signal, which is not chemically equivalent to this CH2, so that should give us a different signal, which is not chemically equivalent to this CH3, so we should expect 3 signals. So we're going to count this quartet as a particular signal that was broken up into smaller subpeaks. This singlet is a signal that corresponds to a particular set of hydrogens, and this triplet is the 3rd signal. So we need some kind of framework to understand why a set of hydrogens would be, or a particular peak that's associated with a set of hydrogens would be broken down into smaller subpeaks. And we'll talk about that now. And so what I want to introduce now is what we call the N+1 rule. And what that says is that any set of hydrogens with n adjacent hydrogens is going to be split into N+1 peaks. So let me put that into more simple terms. If we look at this CH3, you want to look at the carbon right next door and count how many hydrogens are on that carbon. On this carbon, there's 0 hydrogens. 0 plus 1 is 1. So this CH3 should give us a single peak or a singlet. So this CH3 corresponds to this singlet. Here we have a CH2 and a CH3. 3. If we look at this CH2 and we look at the carbon next to it, there's 3 hydrogens. 3 plus 1 is 4. So we should see 4 peaks or quartet. So this CH2 is associated with this quartet, right? Because by the n+1 rule, we should expect to see 4 peaks since there's 3 hydrogens next door. And by similar virtue, we have this set of hydrogens. Next door to it is a carbon that has 2 hydrogens. 2 plus 1 is 3. So we would expect a triplet from this set of hydrogens, which is what we observe here. So this peak comes from this CH3. This peak comes from this CH2. And this peak comes from this CH3. Remember that it's the number of hydrogens on the carbon next to that set of hydrogens that dictates the splitting. So this is a CH3. We're not looking at these 3 hydrogens to determine splitting. We're looking at these 2 hydrogens which are next door. That's very important. Okay, so let's briefly talk about why we get a particular splitting pattern. So if we look at this HA, it has 1 hydrogen next door, right? Remember we said for each hydrogen you can have an alpha state, which is aligned with the magnetic field, or we can have a beta state. So if we assume the HA is an alpha state, we have 2 possibilities. We can have up-up, or we can have up-down. So a single peak is split into 2 peaks, which would be our doublet from having 1 hydrogen next door. So 1 hydrogen next door appears as a doublet because that HB can be either aligned with the field or against the field. So we can have what we call alpha alpha or alpha beta. There's 2 possibilities that are equally likely. If we look at the next possibility though, if we're looking at just a signal from HA, right, we can have HB and that can be up or down, and we can have this HB which can be up or down. So if we assume HA is up, we can have up, up, or we can have 2 redundant possibilities, which we can have up, down, or down, up, or we can have down, down. So we get a 1 to 2 to 1 ratio, which is a triplet. And in the last possibility, we can have alpha, 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 or we can have beta, alpha, 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 beta, alpha, etc. Long story short, what you end up with is a 1 to 3 to 3 to 1 quartet from 3 adjacent neighbors. So what's happening is the spin from the hydrogen next door is affecting the spin or the magnetic field that this hydrogen feels. Okay, so let's look at some more spectra and understand spin-spin splitting and rationalize what we're seeing here. Okay, so here we have 1 hydrogen on this carbon. Here we have a CH3. Here we have a CH3. First off, we're going to expect 2 signals because these 6 hydrogens are chemically equivalent, but they're not chemically equivalent to this particular hydrogen, so we should expect 2 signals, right? This hydrogen is adjacent to 6 chemically equivalent hydrogens, right? 6 plus 1 is 7, so we should expect a septet, and if we count here, we have 1, 2, 3, 4, 5, 6, 7. So we see a septet here that we would expect to integrate to 1 hydrogen. If we integrated this entire set of peaks, we would get 1 hydrogen. Here, if we integrated these 2 peaks, we would see 6 hydrogens, which makes sense, right? Because these 6 hydrogens are adjacent to a single hydrogen, so these would get split into a doublet. And the chemical shift also makes sense, right? Because this peak corresponding to this hydrogen is further to the left because it's directly bonded to an electronegative bromine. Okay, so let's go the other way, right? Let's look at a structure and anticipate what we'll see. First off, you want to look at chemical equivalence, right? We have a CH3, which is not chemically equivalent to a CH2, CH2, CH3, right? So we should expect to see 4 signals from the 4 different sets of non-chemically equivalent hydrogens, right? In terms of chemical shift, we would expect these 2 peaks probably to be shifted the furthest to the left. So these would be the most d-shielded because they're closest to the oxygen. This would be the next most d-shielded, and this would be the furthest to the right or the most shielded. This would be the most electron rich because it's furthest away from this electronegative oxygen, right? Let's talk about integrals. We have 3 hydrogens here, so we'd expect an integration of 3 to 2 to 2 to 3. This would be, the splitting is the most important thing. This is next to a carbon bearing no hydrogens, so this would be a singlet. This is next to a carbon bearing 2 hydrogens, so we'd expect a triplet here. This is next to 5 hydrogens, so we would expect a sextuplet here, and this is on a carbon, this is next to a carbon bearing 2 hydrogens, so we'd expect a triplet. So we should see a singlet, triplet, sextet, triplet. So let's look at the actual spectrum, see what it looks like. We get a triplet, a singlet, a sextet, and a triplet, right? Just as we predicted. So this singlet must be associated, or this set of hydrogens must be associated with this singlet. We have 2 different triplets, right? We have this triplet and this triplet. This one integrates to 3 and is the furthest to the right, the most electron rich. This one's the furthest to the left and integrates to 2. And the one in the middle is the sextet right there that also integrates to 2. Okay, so what I want you to get really familiar with is the various regions in the NMR where we see different kinds of hydrogens, right? So aldehyde peaks are here between 9 and 10, that's this hydrogen. Aromatic peaks, or sp2, are going to be here between 6 and 8. So we see 2 doublets here for this set of hydrogens and this set of hydrogens. These are chemically equivalent because they can be split by a mirror plane. Then we have a CH2, which is next to electronegative atom, so that's going to be pretty far to the left. And then we have a CH3 that's not next to an electronegative atom, so that's going to be in the 0 to 2 range. There's one exception to the n+1 rule, and that's OH peaks this hydrogen will not split an adjacent neighbor, right? So, and what we usually see is a broad peak. So this is our OH peak. Then this is only next to 2 hydrogens, so this would be a triplet. This is next to 5, so this would be a sextuplet, and this is next to 2, so that would be a triplet. We see a triplet, sextet, and a triplet. So generally, OH peaks do not split peaks, and this is due to the fact that this OH is rapidly switching out that hydrogen with other OHs and other molecules. Okay, so to summarize, we can use integration to determine the ratio of peak areas, which gives us the ratio of the hydrogens in the molecule that we're studying. The n+1 rule is really important. N is the number of nearest neighbor hydrogens, and that's going to split that peak into n+1 peaks, right? So if we have 0 nearest neighbors, we're going to get a singlet. If we have 2 nearest neighbors, we're going to have a triplet. If we have 3 nearest neighbors, we're going to have a quartet. If we have 1 nearest neighbor, we're going to get a doublet. We can combine chemical shift, integration, peak splitting to get lots of information about unknown organic compounds. What I want you to be able to do is use all this information to predict a structure from a spectrum and predict a spectrum from a structure.